Hi guys, good morning. It's another lovely Tuesday and today we're going to be doing physics. Okay, so before we go into the class for today, I just want to share some facts, fun facts with us. I want you to sit back and try to understand. Now, I'm going to show you the picture of a woman and I want you to try to, think about who she is and see if you can figure out her name. Okay, so guess and try. Okay, so let me tell you who this woman is. Her name is Maria Gilbert Mayer. She's known as Maria Mayer. Okay, so what was her contribution to daily life and what has she done in physics and across science? So let's just look at some few things that she has done. Okay, have you ever heard about the nuclear shell model of the atomic nucleus? Okay, if you haven't, you're hearing about it now. She was the one that brought about the nuclear shell model of the atomic nucleus. Now, it's a model that uses the Pauli's exclusion principle to describe the structure of the nucleus and talk about the structure in terms of the energy level of each level of the of the nucleus. So she was accorded so much credit for this particular discovery and this particular theory that she brought forth. Now, but she did so many other things. I'm not sure you've heard of it, but let me just tell you about them if you haven't. So what else did she do? She worked out the theory of possible two-photon absorption by atoms. So she postulated another theory, worked out another theory that said that it's possible for an atom to absorb two photons of either the same frequency or different frequencies, and then that excites the molecule to a higher energy state from the actual state it was in previously to a higher energy state. So her work cuts across different fields of science, and because of these things that she discovered and worked on, she was the second woman to be awarded the Nobel Prize in Physics. Isn't that awesome? The first woman is also very popular, and we'll talk about her as time goes on. So I just want to say that you could be on this list also. You could be awarded the Nobel Prize in Physics or chemistry or science. So you just need to find out what you're good at and work with it, and who knows. Okay, so that's that for fun facts for today. I want to now tell you what you need to know today. Of course, I want you to be able to define work, energy, and power. I want you to be able to also state the principles that govern these concepts and the calculations involved in these concepts. Okay. Let's start with work. So work, energy, and power. Let's start with work. What is work? So in English language, when you say I have a lot of work to do, what does that mean? It means you have a job to do or you have some things you need to do, right? But in physics, when we say work is defined as the product of force and the distance moved in the direction of the applied force. So that's work in physics. It takes into account a force and the direction, the distance in the direction of that force, the distance moved in the direction of that force. So it's the product of those two concepts. So for example, if we want to put it mathematically, if we say W is work done, we can say F is applied force, and we can say S is distance covered. Now, in essence, that means that our work done is F times S. And the unit of work done, SI unit of work done is joules. Take note of that, it's joules. You can have kilojoules and megajoules, but our SI unit is joules, okay? So that's that for work done. Now let's talk about work done by an inclined force. Now, a force that isn't applied directly to the horizontal, but is applied as an inclined at an angle to the horizontal. Now, if the force F responsible for moving a body B along a horizontal plane is applied at an angle of theta degrees, the resultant force acting on the body is F cos theta. Let's take a look at this diagram. So you can see that this body You can see this body B, and you can see there's a force applied to this body B, but it's not applied horizontally, it's applied at an angle theta here. Now this force moves this body through a distance of s meters, okay, through a distance of s meters. So we simply say that in this case, the work done isn't F times S, it's F cos theta times S, because this is the components that we need, F cos theta times S. So W is Fs cos theta. That's another way to write it. W is Fs cos theta. So let's take an example of what we've just said so far. Now, when a force of 400 newtons is applied on the body at an angle 60 degrees to the horizontal direction of displacement, the body covers a distance of 8 meters. Calculate the work done. Okay, what do we do? Let's look at the diagram. So we have a body. You can see the circular part there. That's our body. Now that body, force is applied to that body of 400 newtons, and that force moves the body through a distance of 8 meters. So from this point to this point is 8 meters. Okay, now but the force is applied at an angle of 60 degrees. So the component of the force we are looking at that really affects this body is 400 cos 60 degrees. Take note of that. Don't use 400. 400 cos 60 degrees. Okay, so the horizontal component of the force is what we need. So that's 400 cos 60, which is 200 newtons. You know that cos 60 is 1 over 2. 1 over 2 times 400 is 200 newtons. And of course, the distance covered is 8 meters. The distance covered is 8 meters. So our work done is force times distance, but remember that we need to use 400 cos 60, which is 200, okay? So 200 times 8 is 1,600 joules. So you can always go straight anyway and just say work done is F cos theta, that's 400 cos theta, and just do 400 cos 60 here and just go directly and do that. But I just decided to lay it out like this to help you understand better. Okay, let's move on now to something else. Let's talk about work done in moving a load up an inclined plane. Okay, this might look complicated, but it's not. So just follow me step by step and try to understand. So look at this diagram. I'm going to explain the components that you can see on this diagram. So there's a body. You can see this yellow and green patch here. This is the body. Now the body is to be moved up this inclined plane. Okay, you want to move this body up this inclined plane. Just think about trying to move a crate of minerals onto the maybe the boot of a truck, the back of the truck, and then you use maybe a wooden plank, and then you want to drag that crate of minerals up that plank. Just think about it like that. That's an example of an inclined plane. So you want to move this body up this plane. Now you can see the force, the applied force, trying to move the body up the plane. Okay, now the body applied force has a lot of enemies. I'm sorry to say, but the applied force, I don't know if he isn't a friendly person, because he seems to have a lot of enemies. So let's just look at some of his enemies. Now the first major enemy of any type of motion is friction. Friction is just some kind of evil it's an evil should I say, it's like Voldemort. It's an evil concept, but it's not always evil. When we get the chance to discover, the advantages of friction, you would see that, it can be a good thing sometimes. That's why we say not all setbacks in life are, problems or are evil. Sometimes they work out for your good. So that's just the way friction is. But in this case, friction is our enemy here. So frictional force is trying and is saying, no, I'm sorry, this body is not going anywhere. And the applied force says, no, I am going to move this body. So the frictional force is working in the opposite direction. The applied force is saying, no, I'm going to move this body up the plane. So that's one enemy. Now, the second enemy here is the weight of this body. The weight of this crate of minerals or whatever it may be is acting downwards. And it has a component that acts in this direction. I will show you that in the next diagram. But let's just look at this. Now, the reaction of the inclined plane is also going upwards. So that's another component going upwards in this diagram. We also have the height of the inclined plane and all of that. But let's now talk about the work done. Now, work has to be done against the weight of the crate. Let's just say the body is a crate here. So work has to be done against the weight of the crate, and work has to be done against friction. Okay, so the total work done is the work done against gravity, which involves the weight of the body, and the work done against friction. The work done against friction. Okay, so let's simplify the diagram a little and let's see. So let's see. P here is the applied force. It remains the applied force. W here remains the weight of the body. R here remains the reaction of the inclined plane to the weight of the body, and F here remains the frictional force, and theta remains the angle of inclination. Now, the only new thing I have added here is this Wx that you can see here. Now, this is the component of the weight of the body along the inclined plane. Now, like I said, the applied force has to overcome the frictional force and the component of the weight along the inclined plane. So the applied force has two things to overcome. So let's just list out everything again. P is the applied force. Wx is the component of the weight along the plane, which is actually W sine theta. Okay, then the frictional force is mu r. Mu is the component or coefficient of friction. Okay, and r, you know what r is, the reaction of the plane. So mu r is the frictional force. That's how you obtain the frictional force. Then P, in essence, is Wx plus F, because for the applied force to actually succeed in moving this body up the plane, it has to be greater than its enemies. It has to, at least, of course, beat the enemies. So F, it must be plus the addition of F, the frictional force, and the components of the weight along the plane. So that's the value that the applied force must have before it can achieve any goal here. So P is Wx plus F. So work done becomes P times S, which is Wx plus F times S. And of course, Wx is W sine theta and F is mu r. So we have our work done as W sine theta plus mu r into bracket S, where everything has been clearly defined and S is our distance covered. So it's amazing, it's amazing, it's amazing. It's important that you should be able to, if you're asked to find work done and it's not necessarily just the force that's inclined, it's the plane that is inclined, you should also still be able to get the work done. Okay, so don't forget this. Okay, you can practice more and more. Always try to practice on anything you've learned. Practice. Okay, let's move to energy. If I say this boy is full of energy, this girl is full of energy, what does that mean? Another way I can say that is she's full of life. Okay, now very little children, especially toddlers, are very hard to keep up with. They run around the place until they're ready to drop. Okay, you guys are not toddlers, but I know you're also full of energy. So you understand the meaning of energy in English language. Now let's break it down to physics and let's see what energy means. Now, energy is the capacity for doing work. Energy is the capacity for doing work. It's a scalar quantity. That means it has magnitude but no specific direction, and it has the same unit as work done, which is joules. Let's talk about a broad spectrum of energy resources now, groups of energy resources. We have renewable energy. Okay, they are non-exhaustible. Examples are solar energy, wind energy, hydro energy. You can see the diagram there: tidal, geothermal, biomass, and so on and so forth. Okay, then we have non-renewable energy. That's energy that cannot be renewed, that is exhaustible. We have examples there: oil, coal, natural gas, and so on and so forth. So those are the groups of energy resources. But now let's talk about the forms of energy. We have different forms that energy can take. Okay, and these forms can be converted from one form to the other. Let's talk about the forms. We have mechanical energy. Mechanical energy is made up of two different types, and we'll look at that as we progress. We have heat energy. We have nuclear energy, we have sound energy, we have light energy, we have electrical energy, and so on and so forth. Now, I just said that these forms of energy can be converted, from one form to another. For example, you have electricity. Now, electricity from your lines comes into your house and powers your bulbs and produces light energy. Electricity from your lines comes into your house, powers your pressing iron, and produces heat energy for you to remove the creases in your clothes. So you can see the concept of these energy forms being interrelated. Okay, so that's just a slight a small example. As time goes on, we'll talk more about how these energy forms can be converted from one to the other. Now let's talk about the principle of conservation of energy. Very key, very key part of this topic. So what's the principle? The principle of conservation of energy states that energy can neither be created nor destroyed, but can be converted or transformed from one form to the other. We said it can be converted from one form to the other already. Now, but take note that these types of energy or these forms of energy cannot be created and they cannot be destroyed. They are only converted day in and day out from one form to the other. Okay, this is an important principle, so you should try to learn it and remember it as you need to. So mechanical energy is made up of two forms. We said that already. Let's talk about the two forms now: potential energy and kinetic energy. Now, when you hear the word potential, it's the energy possessed by a body by virtue of its position. So if it's at a particular height from the ground, that body has potential. That's what we say. So for example, if a body has a mass m and is held at a height h meters above the ground, its potential energy is simply the weight of the body times the height above the ground. So we know already that the weight of the body is mg times h. So mg times h gives us mgh. So mgh is the potential energy of the body. So try to remember that formula. It's important. Now let's move on to kinetic. Kinetic. From the word kinetic, you should know that it has to do with motion, if you've heard about kinematics. So kinetic energy is the energy possessed by a body due to its motion. So any single body that is in motion has kinetic energy. Okay, so it has kinetic energy. So kinetic energy is energy possessed by a body due to its motion. Now, if a body of mass m is moving with a velocity v, its kinetic energy is simply half mv squared, 1/2 mv squared. Okay, so that's its kinetic energy. Now let's illustrate the conservation of mechanical energy with a diagram now. So look at this object. So it's a body. It's dropped from point A all the way down to point C. Now we're going to talk about the energy of this body at point A, at point B, and at point C. Okay, let's start with point A. Now the body is at a particular height from the ground. This is the ground. The body is at a particular height from the ground. The energy possessed by the body here, just before it begins to move, is potential. So the total energy at point A is just potential energy. So at height HA, the potential energy of the body is maximum. Okay, so the energy there is mgHA. That's the energy of the body. Okay, now by the time it gets to point B, the height has reduced, so the potential energy has reduced, yes, but it has also gained kinetic energy because now it's in motion. So now it's in motion, so it has gained kinetic energy. So the energy here at this point is not just potential now, it's both potential and kinetic. So energy at point B is both potential and kinetic. So the formula for the energy at that point B would be half mvb squared. That's vb is the velocity at point B, plus mghb. That's the height at point B. You can see the height here at point B, hb. Okay, that's the height at point B. Okay, so that's the total energy possessed at that point. Now, when it gets down to point C, just before it touches the ground, it doesn't have potential energy because it's no longer at a height from the ground, but it has maximum kinetic energy. The body actually has maximum kinetic energy at that point. So at point C, we say that the energy possessed by the body is half mvc squared, where vc is the velocity of the body at that point C, just before it touches the ground. Okay, now we've broken down the components of energy at each point of the motion of that body. Now the next thing we need to talk about is how, based on the conservation of energy, the principle of conservation of energy, how does it apply to each of these points? Now, it simply means that the energy at point A, based on our principle, since we said that energy is not created or destroyed, it's only converted from one form to the other. It means the energy at A must be equal to the energy at B, and it must be equal to the energy at C. Okay, so that in essence, it means that mgHA must be equal to half mvb square plus mghb, and it must be equal to half mvc square. So that's our concept. That's what conservation of potential and mechanical energy, or energy in general, actually helps us to understand. Now, but I want you to understand something else. Okay, follow me, understand something else. I said that at point A, the potential energy is maximum, right? Then we said that at point B, the potential energy has reduced, okay? Now, I want you to take note that the reduction in potential energy from point A to point B is the same, follow me, is the same as the kinetic energy that the body has acquired by the time it gets to point B. The potential energy reduces from A to B, but that reduction is exactly the same as its kinetic energy as at that point B, because as the potential energy was reducing, the kinetic energy was increasing. Isn't that amazing? So that means that half mvb square, which is the kinetic energy at point B, is equal to the potential energy here, mgHA, minus the potential energy here, mghb. So that's another useful formula that you should take note of, and you never can tell when you would need to recall it and use it for some calculations. So let's look at an example now. I have already taken the liberty of putting the diagram there for you, okay, but in your own scenario you would have to draw the diagram. Okay, so a stone of mass 2 kg is released from a height of 12 meters. At what height would the velocity be 5 meters per second? So I took the liberty to put point A here. That's where the body was released, and point B where the velocity has become 5 meters per second. Now let's apply our principle. Now let point B be the point at which the velocity is 5 meters per second. Now the height at point B is h of B. Okay, so you've seen that already from the diagram. Now the total energy at A, based on our principle of conservation of energy, the total energy at A must be equal to the total energy at B, right? This energy here must be equal to the energy here. Okay, now but the energy here is potential in nature. Okay, the energy here is potential in nature, while the energy here is both potential and kinetic. Both potential and kinetic. So let's look at that. Total energy at A is 240. Why is it 240? Let's try to get why it's 240. It's 240 because mgh is mass 2 times g. Let's say our isolation due to gravity is 10. So 2 times 10 is 20 times the height, that's 12. Okay, so 2 times 10 times 12 is 240. Okay, so that's how we got the total energy of A at A as 240. It's the total potential energy. Now 240 is equal to the kinetic energy at B plus the potential energy at B. Okay, so we have 240 equals half times m, which is 2, times the velocity at point B, which is 5 meters per second, so 5 square. So half times 2 times 5 square. Now plus the mass is 2, gravity here, we're using 10 for our acceleration due to gravity here, and we do not know the heights. Of course, we are looking for, they said at what height would the velocity be 5 meters per second. So we are looking for this height. So let's just say HB. Now let's evaluate further. 2 cancels 2 out here, so 5 square is 25. 2 times 10 is 20 HB. So to get HB now, we're going to rearrange, and we'll say 20 HB equals 240 minus 25, which gives us 215. So HB here becomes 215 over 20, which gives us 10.75 meters. Okay, so the principle of conservation of energy is important, and you should try to apply it and recall it, when you need it. Okay, All right, so let's move on. Let's move on. Okay, so I want us to just go to power now. Let's move on to power. Now, power, what is power? And if we're dealing with power in English, we say power is having, ability, or it's almost like capacity to do something. The person has the capacity to do something, or the ability to do something, right? That's English language, power. I have power. I am powerful person. Now, in physics, however, power is the rate of doing work. Power is the rate of doing work, or the amount of energy transferred per unit time. Power is the rate at which work is done, or the rate of doing work, or the amount of energy transferred per unit time. So power takes into account the work done and the time taken, or the energy transferred and the time taken. So there are two basic concepts involved when we're dealing with power. So power is work done or energy transferred over time taken. So the SI unit of power is also watts. So when you hear 300 watts, that's power in physics, okay? Okay. Power can also be expressed as a function of the velocity of the body doing the work. We can derive a formula that relates power to velocity. Let's look at that. We already said that. Let's take the first part, work done over time taken, okay? Now, but power is work done over time taken, but work done is force times distance, if you remember. Work done is force times distance, okay? So, force times distance over time now. Now, but distance over time is what? Of course, distance over time is speed. You know that displacement over time is velocity, but let's just use them interchangeably. We're not talking much of the direction now. We're focused on the magnitude. So force times velocity is power. So power can also be expressed as F times V, FV. Apart from saying work done over time taken, you can also say power is force times velocity. So remember these formulas, and you can try to even derive them. It's a very short one to derive, not difficult at all. So you can also put that knowledge in your brain box. Okay, so let's take an example. Calculate the power output in watts of a machine that lifts a 50 kg crate through a height of 20 cm in 1 minute. So let's take a list of everything we know. We have to find the power. The mass of the body is 50 kg, the height is given, the time is given. Let's write everything out. So the mass is 50 kg, the height is 20 cm, but we need to convert that to meters by dividing by 100, because 100 cm is 1 meter, so that gives us 0.2 meters. Okay, that now leads us to G. We can use G as 10 meters per second squared, and then our time is 1 minute, and 1 minute is 60 seconds. Okay. So power is energy transferred over time taken. Remember that? And in this case, the energy is potential here. So mgh. Okay, so mgh over T, and that gives us 50 times 10 times 0.2 over 60. Okay, and so our answer is 1.67 watts. 1.67 watts. Take note that you can be given questions in different dimensions. You can be given something that involves velocity, and then you should use the formula force times velocity. You might not even be given the parameters directly. You might be given something else, and you need to apply, first of all, apply the equations of motion. We've talked about that, and then use that to find the unknown that you need, maybe distance to use in the formula, or probably velocity to use in the formula. So just be proactive and know when to apply other equations before moving on to the solution. Okay, I believe you should be able to do it. Okay, so let's summarize quickly everything that we have discussed today. We talked about work, and we talked about work in terms of force that is applied at an inclined at an angle, and we talked about work in terms of a force applied on an inclined plane. We discussed energy. We talked about energy as the capacity for doing work, and we talked about the types of energy. the groups of energy resources. Then we talked about the forms of energy, the forms that energy can take. We talked about the principle of conservation of energy. That's a very important one. Do not forget that energy can neither be created nor destroyed, but can be transformed, from one form to the other. Then we talked about power, and we said, power is a rate of doing work, or the rate at which energy is transferred. We said power is work done over time taken. So just take a minute to, recap on everything that you have learned today, okay? And then in that light, I want you to practice. So I'm going to give you a question now. Look at this question and just try to calculate what you can see on your screen. If you do it properly, you should get the answers that you can see on your screen. Okay, so you should get these answers. So leave me a comment if you're able to achieve those answers. Then you can also visit quizzes.com and play games on force, work, energy, and power. I hope you've had a lovely class today, and I hope to see you same time, same day next week. Remember to like the video and share to your friends, okay? And don't forget to subscribe for weekly updates. Have a lovely day. Bye.